So pretty much already told you what we're doing. pH scale, so we're going to show you how to go from hydronium to pH, super simple. Then I'm going to show you how to go the other direction, so how to go from pH to hydronium. We'll talk about hydroxide and POH and their connection. It's the same calculations as what you see in part A and B, just it's hydroxide rather than hydronium. I'll summarize things, so I'll just give you a little table that you can follow if you choose to do so. The only new thing that we're doing today is sig figs. If I taught you last year, I told you, just round all your answers to 2 decimals. Good enough when it comes to pH calculations. This year, we're going to be doing things a bit differently. I want to show you how proper sig figs work. That's the only new thing. So hopefully we can get a little bit better of an understanding of pH scale. Anybody doing Math 12 right now? Okay. If you're doing Math 12, you may have been exposed to logarithms. Okay, maybe you haven't got that far into the course. I'm not sure. Here's how logarithms work. Okay, so if I were to take a number such as 10 and I square that, 10 squared is equal to, okay, 100. Oh, you guys are fast. You did that without calculators. That was amazing. Okay. If I were to take the log of 100, what I'm really asking is, to what power, and please forgive me here, I'm not a math teacher, so I might not use the perfect terminology in explaining things here, but really what I'm asking here is, to what power has that base unit of 10 been raised to? So if I keyed that into my calculator, I take the log of 100, I get an answer of 2. If I took the log of 1,000, okay, that would give me a value of 3. Okay, so that's because 10 cubed is equal to 1,000, and so on. In fact, you know what? I'm going to write that out here. So if I said the log of 1,000, okay, there's a good reason for that. Now, what I'm really trying to say, or I'm going to go over this in a second here, this number here is 10 times larger than that. Okay, just like that is 10 times larger than that. Okay, so I'll come back to that. pH scale is a way of expressing concentrations of hydronium ions based on logarithms. So this is what we're going to use to do these calculations here. We're going to take the negative log of the hydronium concentration. Now, because the pH scale is a logarithmic scale, each 1 unit change in pH value represents a 10-fold change in the concentration of hydronium ions. So if you go from a pH of 7 to 6, 6 is 10 times more concentrated. pH of 7 to 5, well, 5 is 100 times more concentrated, and so on. Now, it's a little different from the example that I just gave you because we're going to be talking about negative log values. Okay, but it's kind of related in some respects here. Okay, now I'm going to go down and just cover this table in just 1 second here. One thing I do want to say, though, is that because you're going to be using my calculator on your mid-unit test, it's a really good idea for you to grab my calculator and to get some practice, okay, doing these types of calculations. Okay, so it's important that you perform with my calculator, not necessarily yours. So I'm going to give you an opportunity to grab one of mine if you would like to. You can do that right now. I would strongly, strongly encourage you to do it. I've got them in the box as well. Just make sure that if it has a case, it gets put back in the box. No case, it goes on the wall. There's a very good reason why I'm having you use my calculator. Okay, so I'll get to that in just a moment here. So what I want to do is I want to start off by taking a look at a pH of 7. First of all, pH means the potential of hydrogen or the potential of hydronium. It is a measure of how concentrated, okay, the hydronium or hydrogen ion concentration is. POH is the potential of hydroxide. So if we start off with a neutral pH, and please forgive me my highlighter, okay, because of the green background, it's not going to highlight the greatest. But if we start with a pH of 7, that means we also have a pOH of 7. So that means that hydronium is 1 times 10 to the minus 7 moles per liter hydroxide. It says 10 to the minus 7, but it's the same thing as 1 times 10 to the minus 7. So what I want to do, let's take a look at what happens when we go this direction here. So if we have hydronium concentration of 1 times 10 to the minus 6, we have a pH of 6. 1 times 10 to the minus 5 is 5, and so on. Now here's where it's kind of weird. Larger concentrations of hydronium means a smaller number for your pH. So smaller number means more. Okay, so this is really important that you understand this. A smaller pH number means more hydronium. Now that also means less hydroxide. Okay, so we'll see that hydroxide went from 10 to the minus 6 to 10 to the minus 8. And we can see that the pOH value, okay, as hydroxide concentration decreases, our pOH increases. So here, larger number means less. Okay, now what I want to do is I want to go right to the far left-hand side. Now, we generally learned, I think, back in Science 10, that pH goes from 1 to 14, right? You might have been told 0 to 14, probably 1 to 14, right? Okay. You ever seen that before? A pOH of, and I think I'm just going to use a different color here. I'll do it this way here. A pH value of 0. Now, 14 we're accustomed to, that's fine. pH. A pH of 0. Okay, and then look at this, -1. Okay, we've not seen this before. Okay, so what I'm saying here is that pH, pOH, we can have values, okay, as small as 0 or even into negative values. You might wonder, okay, well, how is that possible? If I got 12 molar hydrochloric acid, okay, so that's what I buy from the supply company. I then dilute that so that it's safe for my students to use, but it's 12 moles per liter. If I do the calculation, which I'm going to walk you through in a moment here, but if I calculate 12, okay, I'm going to convert that to hydronium. So I'm going to make that, okay, oh, sorry. What did I say? Oh, sorry, 12 molar. Okay. 12 molar hydrochloric acid has a pH of minus 1.079, minus 1.079. So if you're starting to get negative values, that just simply means that we have a very strong acid, or if we're talking about a base, it's a very strong base. So negative values mean very, very large, high concentrations. Now, as we go in this direction here, okay, well, what we can see here, of course, is that this time our pH values are getting larger. Larger means less. pOH is getting smaller. Smaller means more. So far, any questions? Some problem. In apple juice, hydronium concentration is 4.8 times 10 to the minus 6 moles per liter. What is the pH of the juice? First of all, this isn't asked in the question, but acid or base? Acid or base? Okay, it's going to be acidic. So that value right there is acidic. Because it's greater than 1 times 10 to the minus 7 moles per liter. Now, it doesn't tell us what the temperature is. Just assume it's 25 degrees Celsius unless I tell you otherwise. Okay, so super simple calculation here. So my pH is the negative log of my hydronium concentration. So that would be the negative log of 4.8 times 10 to the minus 6 moles per liter. All right, now, this is the reason I had you grab my calculator. Okay, your calculator probably works the exact opposite from mine. So here's how you do it in my calculator. So what you'll do is that you will key in 4.8 times 10 to the minus 6. So that's your step one. So 4.8 EE 6, and then you want to hit that plus minus key just to the left of the equals key. So 4.8 EE 6, turn that into a negative 6. Then I'm going to select the log key. That's my second step. So that's up at the top. Okay, so third button to the right at the top. Now, if I do that, I'm going to have a negative value, and I want to turn that negative value into a positive value. So again, just to the left of the equals key, there's that plus minus key. You're going to select that. If I do that, I'm just going to round my answer to 2 decimals. That's what I told you to do last year. I'm going to explain the sig figs pretty soon, but we'll say this is good enough. Get an answer of 5.32. Now, for those of you at home, of course, you probably have your own calculator. Okay, so what I'm going to have you do is I'm going to have you take this, enter it exactly the way you see it. So your calculator will work in the exact reverse. So you're going to key in minus log 4.8 times 10 to the minus 6, and then either the equals or the enter key, and you should get the same answer. All right, so we already said that, that this solution is acidic, and we also see that our pH value is 5.32, so that is less than 7. So again, another indicator that it's an acid. Okay, so I just showed you how to go from hydronium to pH. I want to show you the reverse calculation. So we're going to use this right there. Our hydronium concentration is the antilog of the negative pH. Now, the antilog on most calculators, including mine, you will go second function log. On my calculator, it has a 10 to the x, okay, signified right above that. That is your antilog. Okay, now on some calculators, it might be a different key. Okay, for those of you at home, this might be a little bit frustrating trying to find your antilog key. Because, and quite honestly, I probably won't be able to help you with this, at least not doing this remotely. Okay, if you are having problems, let me know and I will try to work with you though. Okay, so let's just jump into the sample problem. Find the hydronium ion concentration of a solution with a pH of 8.412. Hydronium concentration that is going to be equal to the antilog of the negative pH, which is the antilog of negative 8.412. So just like what I showed you before here on my calculator, what we always do is that you my tablet just, there we go, came back. So you're going to enter the value first and then take the antilog. So what I will key in is 8.412. What the hell's happening with me? Oh, I can see what's going on. Somebody loosened up my connector here. Make a great recording. Okay. So then I want to make that a negative value. So that's my next step here. I'm going to hit that plus minus key. And then for my third step, I'm going to take the anti-log function. On my calculator, you go second function log. Now, if you're using your own calculator, just reverse the order. Okay, especially those of you that are at home, you'll go second function log, then you want to select the minus key and then 8.412 and then equals or enter. And if you've done this correctly, you will end up with, I'm going to round that to 2 decimals, 3.87 times 10 to the minus 9. Anybody having any problems so far with this? Yes, awesome. It's not giving you the right answer? You got 4. Oh, hang on a second here. Let me see what this one. So 8.412, I'm going to make that a negative value, second function log. Okay, this is a good one. So on my calculator, and for those of you that are at home, and I'm glad that that I just got asked about this, you get an answer that just goes 0.000000, and then you have a 4 at the end. So here's the thing, is that the calculator, because it can only display 8 digits, what it will do is that it will actually round. Okay, it should automatically convert to scientific notation. It doesn't do that. What it does is that it just rounds things off. Okay, that's not helping us a huge amount. So what I'm going to do is I'm going to go second function and then select 5. Just above the 5 key, it says SCI. Okay, now that converts it into scientific notation for me. And now I have the answer that you see right here. Now, if you're at home or if you're using your own calculator, okay, this is more challenging to convert it into scientific notation. You actually have to put your calculator into scientific notation mode. Okay, I can help students with that later on this period if necessary. That doesn't come up very often. That just happens from time to time where the calculator does that. Anything else? Okay, does that make sense? Okay. Okay, so now we're going to deal with hydroxide and POH. The good news, though, is that the calculations are identical. So our POH is the negative log of the hydroxide concentration. So it's the same thing as our pH calculation. And to go the other direction, to go from POH back to hydroxide, we take the anti-log of the negative POH. I'm not even going to bother doing sample problems for that, just simply because I think it's so straightforward and I think you're catching on to this. Okay, so the next thing here, the mathematics of logarithms results in this relationship between pH and POH for a solution at 25 degrees Celsius. Now, we get different values at different temperatures, but at 25 degrees, the pH and the POH added together give us a value of 14. Okay. So what I want to do, I want to prove something here. So let's just take a look at our Kw expression. It's the concentration of hydronium times hydroxide. Hydronium times hydroxide. Now let's say I want to take hydronium and I want to convert that to pH. Okay, so if I wanted to do that here, I would just take the negative log of that, right? So the negative log of hydronium would look like that. That gives me my pH. And then, if I wanted to take my hydroxide and convert that to POH, I would take the negative log of hydroxide. That gives me that. Now, that is something that is called our pKw. pKw. So really, the P just simply means the potential of, or in other words, we took the negative log of it. Okay, and taking the negative log of our KW value, that gives us pH plus POH. So in other words, that right there. And we've already determined that at 25 degrees, that value is equal to 14, right? So what I'm really saying here is that that is our pKW at 25 degrees. So you might see that term come up from time to time. I'll call something the pKW. Okay, that's what I'm talking about. Summary of calculations. If when you start working on your worksheet, you want to refer to this, this might help you. I'm not going to explain. Okay, I have all of this stuff already here. So sig figs. This is where it gets kind of interesting. Didn't teach this to you back in Chemistry 11 because, oh boy, it's another sig fig rule. We already had enough of that crap last year, right? So this year, you're expected to know how to round your answers off. Okay, and I want to say, first of all, is that this is not even close to perfect. It's just the best that we can do with this. So since hydronium concentration, okay, well, if we had a value of, let's say, hydronium is 5.28 times 10 to the minus 5 moles per liter. Okay, well, we would say that the 5.28 is the significant part, right? So we would say 3 sig figs, right? But what about this part right there? The times 10 to the minus 5, that's not significant, right? Because all it does is it tells you the number of zeros that come before the 5.28. So a bunch of zeros, then 528. Okay, so the times 10 to the minus 5, I want to say it again, it's not significant. The part that's significant is the 5.28 part. Okay, so let's say we were trying to convert this from hydronium to pH. So we know that it's the negative log of our hydronium concentration. So that right there. So here's what I'm going to do is I'm going to show you what happens when we take the negative log of the 5.28 part, the part that is significant, and then we'll take the negative log of that part there, which is not significant. So when I take the negative log of the 5.28 part, this is the answer that shows up in my calculator, negative 0.723. When I take the negative log of the times 10 to the minus 5, the part that is not significant, we have this big number here. And now when I put both of these values together, we get that right there, 4.277. Now this isn't normally the way that we would do this or solve this, by the way. I'm trying to make a point here though. Okay, so the point I want to make here is that most of that number, most of that value came from that, the part that's not significant. So what we're going to do is we're going to say that this is the part that is significant. Now, this might seem really weird, okay, and it's far from a perfect solution. It's just the best thing that we can do given this situation. So we're going to say that the part before the decimal is not significant, and the parts after the decimal, they are significant. So here's what I would do is I would say, okay, well, we have 3 sig figs, so we're going to round our answer to 3 decimal places. 3 sig figs means 3 decimal places. So for pH, only the digits after the decimal are significant. Now, if I wanted to go in the reverse direction here, I would say, okay, well, I've got 3 decimal places. That means I want 3 sig figs when I calculate hydronium concentration. Okay. Are there any questions? Again, I'm just going to go back to my online group here to see if there's any questions there. Why did you write 1.8 inside the log, not 4.8. It might have been my, it's been doing some weird things. So let me just take a look here. Yeah, that's just this right here. So I did take the negative log of 4.8. I think that's what you're getting at, Joseph. Okay, it's just, again, it's my crappy handwriting. It doesn't look much like a 4. I understand. Okay, see if there's anything else there. Okay. So I'm just going to stop my recording here.